Hello, this is Richard Hammack's Calculus 1 course. Today we begin part 5 of the course on integration. Roughly speaking, part 5 and the topic of integration concern the process of running differentiation in reverse and the consequences of doing that. But our next two lectures follow so naturally from our work on differentiation that I'm going to postpone giving an overview of part 5 until after we've done them. So with that, let's start lecture 39 on antiderivatives. I begin by outlining our plan. Given a function f of x, we know how to find its derivative. We're very familiar with this process. Given an f of x, through the process of differentiation, we can find the derivative f prime of x. Beginning today, we run that process in reverse. From f prime of x, we'll run backwards and reconstruct f of x. And this process of running differentiation in reverse is called anti-differentiation, or more commonly, integration. So today's goal, in a nutshell, given f prime of x, find f of x. Run differentiation in reverse. I'll begin by giving a definition that gives a word to this goal. A function big F of x is an antiderivative of little f of x if big F prime of x equals little f of x. So here's the picture. Given a big F of x, if you differentiate it and get a little f of x, that little f of x, of course, is called the derivative of big F of x. But our definition here today says that this big F of x is the antiderivative of little f of x. An antiderivative of little f of x is a function big F of x, which if you differentiated it, would give you little f of x. And today we'll be looking at the process of finding an antiderivative of little f of x, going backwards to get this big F of x, which is the antiderivative of little f of x. And again, that process is called integration, and we would say we're integrating this function, little f of x, to get big F of x. So I've just restated that definition up at the top of this slide. A function big F of x is an antiderivative of little f of x. If you differentiated it, you would get little f of x. So as indicated here, this is the antiderivative of little f of x. As an example, let's see if we can find an antiderivative of the function little f of x equals 2 times x. So I'll duplicate this picture. An antiderivative of 2 times x would be a function over here, maybe we don't know what it is yet, but if we differentiated it, we'd get 2 times x. Well, you don't have to look very hard because big F of x equals x squared would do the job. If you differentiated that, you'd get 2 times x. So big F of x equals x squared is an antiderivative of 2x. But it's not the only one. Notice that you could also have big F of x equals x squared plus 1. And when you take the derivative of that, you get 2 times x again. Or there's nothing magic about the number 1. It could be any number, like the number 5, etc. So looking at it this way, in general, any function big F of x, which is x squared plus c, where c is a constant, that's an antiderivative of 2 times x. If you differentiated any function that looks like this, you'd get 2 times x. So we actually see here that the function 2 times x, it doesn't just have one antiderivative, it has infinitely many antiderivatives. big f of x equals x squared plus c is an antiderivative where c could be any real number. So to summarize, the antiderivatives of f of x equals 2x are the functions big f of x equals x squared plus c, where c is a constant. And I have these graphed here. The functions big f of x equals x squared plus c, that would just be like, a parabola. Here's big f of x equals x squared plus 0. And here's big f of x equals x squared plus 1. This one's big f of x equals x squared minus 1, and so on. Infinitely many functions, big f of x equals x squared plus c. I've only drawn 4 of them here. Obviously, we can't draw them all. Here's another example. Let's find the antiderivatives of the function f of x equals x squared plus 5 cosine x. So those are the functions. We don't know what they are now, but if we differentiated them, we get x squared plus 5 cosine x. Well, a little bit of reverse thinking can get you that antiderivative, could fill in the question mark. You'd expect this to have several terms, this antiderivative, and the derivative of the first term should give you the x squared. Well, you play around with that for a little bit and you figure out that 1/3 x cubed, its derivative would be 1/3 3x squared, which equals x squared. That would give you the x squared here. And the next term, its derivative would have to be 5 times cosine x. A little reverse thinking would tell you that 5 times sine of x, that has a derivative, 5 cosine x. And then we add on a c. So the antiderivatives of big f of x, of x squared plus 5 cosine x are the functions big f of x equals 1/3 x cubed plus 5 sine x plus c. And there are infinitely many of them, one for every value of c. So there we go. Those are all the antiderivatives of x squared plus 5 cosine x. So I'm going to make a definition that's very close to the definition of an antiderivative, but it has a shade of meaning difference. If f prime of x equals little f of x, that is, if big f of x is an antiderivative of little f of x, then this big f of x plus c, like this thing that we had up here, that's called the indefinite integral of f of x. So we would say that big f of x equals 1/3 x cubed plus 5 sine x plus c is the indefinite integral of x squared plus 5 cosine x. So notice that big f of x plus c, it stands for the set of all antiderivatives of f of x. So that's the difference in the meaning of indefinite integral and antiderivative. An antiderivative is just one function whose derivative is your little f of x. The indefinite integral is the set of all of the functions big f of x plus c that are antiderivatives of your little f of x. And we have a strange notation for this. To indicate that big f of x plus c is the indefinite integral of f of x, we write that as follows. We have an elongated s symbol that's read integral. So the integral of f of x dx equals big f of x plus c. So whenever you enclose a little function f of x between an integral sign and a dx, that's a little notational package that says this is the indefinite integral of the little f of x. It's the set of all antiderivatives of little f of x. So for instance, We figured out all of the antiderivatives of 2x were x squared plus c on the previous slide. So the integral of 2x dx equals x squared plus c. That's the indefinite integral of 2x. And recycling the problem up here, the integral of x squared plus 5 cosine x dx is 1/3 x cubed plus 5 sine of x plus c. That's the set of all antiderivatives of x squared plus 5 cosine x. That's the indefinite integral of x squared plus 5 cosine of x. So to summarize what we've done so far, we have this process of differentiation, which would take a function big F of x plus c and take its derivative. You do d dx of it, and you get another function, we'll call it little f of x. That's the derivative of big F of x plus c. And then we have this reverse process of integration, where you take the integral of f of x dx to get big F of x plus c. So they're reverse processes. And if this ever looks confusing, what I've put in a double box here should always be kept in mind. This is what it's all about. If the integral of f of x dx equals f of x plus c, that's just a fancy way of saying that the derivative of the big F of x plus c equals little f of x. You take the derivative, you get little f of x. You take the integral of little f of x, you get big F of x plus c. These two things, this equality and this one, are really expressing the same relationship between big F of x plus c and little f of x. And I'm going to have a lot to say about this equivalence, and I'm going to probably rewrite it many times and put it in that double box. Let's look at a few examples. How about the integral of x cubed dx? Well, that would be, let's see, that's the indefinite integral of x cubed. It's a set of all antiderivatives of x cubed. And if you do some reverse thinking, you'll realize, oh, if I had 1/4 x to the power of 4 plus a constant, if I took that derivative, that would be 1/4 times 4x cubed plus 0, which would give me my x cubed. So that tells us that this formula, or this equation, is correct. The integral of x cubed dx equals 1/4 x to the 4th plus c. That's the set of all antiderivatives of x cubed. If you take the derivative of this, you're going to get the x cubed. Just like if you take the derivative of this, you get the little f of x. Here's another example. The integral of 2x over 1 plus x squared dx. Now, that would stand for all of the antiderivatives of 2x over 1 plus x squared. Now, this is starting to look complicated, but the answer is actually really simple. What you would need to do is think about, do I know a function whose derivative is 2x over 1 plus x squared? If so, just put it right here and add a c to it. Well, a moment's reflection will tell you that ln of 1 plus x squared has the property that its derivative is 2x over 1 plus x squared. And then we add a c. So we've just figured out that the integral of 2x over 1 plus x squared dx equals ln of 1 plus x squared plus c. So that involves a little bit of reverse thinking, and pretty soon we're going to get more systematic and come up with some equations and some formulas for finding integrals. But right now we're just using the definition of an antiderivative to sort of reverse engineer these problems so that we can come up with an answer. How about this one? The integral of 1 over x, the integral of 1 over 1 plus x squared dx. That would stand for the set of all antiderivatives of 1 over 1 plus x squared, the set of all functions whose derivatives are this. Oh, well, how about tangent inverse of x? Its derivative is 1 over 1 plus x squared, and add on a c, and we've got the set of all antiderivatives of 1 over 1 plus x squared. Okay, let's get more systematic about this. I want to talk about a significant rule for integration that's called the power rule for integration. And as promised, I've put this equivalence in the double box here. Never forget that when you have the integral of f of x dx equaling big F of x plus c, that just means exactly the same as the derivative of big F of x plus c equals little f of x. Using this equivalence, I want to point out that you can reverse engineer a formula for the integral of x to the power of n dx. It has to be this. It's going to be, the answer here is going to be a function whose derivative is x to the power of n. And one way you could get that is, say, it's 1 over n plus 1 times x to the power of n plus 1 plus c. Now, why would that be correct? Because if you take the derivative of all of this, you get the x to the power of n. So it really is an antiderivative of x to the power of n. Because d dx of 1 over n plus 1, x to the power of n plus 1, plus c, would be got as follows. You've got a constant of 1 over n plus 1 here. And differentiating the power, the n plus 1 comes down and cancels with the 1 on the bottom. And x gets raised to the power of n plus 1 minus 1. And then the derivative of c is 0. And you're just left with x to the power of n. So this formula right here is, we're going to give it a special name. We're going to call that the power rule for integration. I'm going to rewrite it. The integral of x to the power of n dx equals 1 over n plus 1 times x to the power of n plus 1 plus c. Now, we'll see a lot of rules for integration, and I want to emphasize on each one that if you're ever in doubt and you want to check it, just differentiate the answer and see if it gives you the function that you were integrating. Because after all, that answer is supposed to stand for the set of all antiderivatives of the function that's right here. And differentiating all of this gives you x to the n in this case. So that's the power rule for integration. Now, I should point out that there's one case where the power rule for integration could derail, and that's if n was ever equal to -1. But then you'd have -1 plus 1 on the bottom, you'd be dividing by 0, and you'd be in trouble. So this power rule for integration, it works provided n is not equal to -1. -1 is bad, it doesn't work for this. This formula just does not work for n equals -1. So, for instance, let's try the integral of x to the 5th dx. According to the power rule for integration, the answer would be 1 over 5 plus 1 times x to the power of 5 plus 1 plus c, and that's x to the 6th over 6. And whenever you work out an integral like this, the set of all antiderivatives of x to the 5th in this case, you can always check your work by taking the derivative of the answer that you got and making sure it gives you what you had here, which is called the integrand. And sure enough, if you differentiate x to the 6th over 6, you get x to the 5th. Here's another example. The integral of the square root of x dx. So here we're looking for the set of all functions whose derivatives are square root of x. Now, just like with differentiation, it pays off to write that radical as a power, because after all, we do have a power rule for integration. And when we write it this way, we see that we could use that power rule for integration. And using it, the n is equal to 1 and 1/2 in this case. So we get 1 over 1/2 plus 1 times x to the power of 1/2 plus 1 plus the constant c. And cleaning that up, that's 2/3 x to the power of 3/2 plus c, which you might prefer to write as 2/3 square root of x cubed plus c. Either one of these is a perfectly sufficient answer. Notice in this fraction over here, it was 1 over 1/2 plus 1. That's 1 over 3/2, and that's 2/3. 2/3 x to the power of 3/2 plus c. I tend to like the variable x, and I use it almost exclusively, but bear in mind that you could have other variables as well, the integral of square root of t, and then dt. Now, notice that instead of dx here, since you're switching your variable to t, it needs to say dt. The integral of square root of t dt equals 2/3 square root of t cubed plus c. This is the answer we had over here, and we're replacing the x with a t. So the change is pretty superficial. Before moving on, I want to point out some things about this dt and the dx. It looks a little strange to have them there, but they're really an essential part of the notational package. Notice over here with the derivative, which we're very familiar with, we had ddx of f of x plus c equals f of x. And in differentiating the big f of x plus c, that ddx had a dx in it, and that was telling us that we're differentiating with respect to x. That's the variable that we expect to encounter, and so we get a function little f of x. And we enclose the function that we're differentiating in square brackets, or maybe parentheses. On the flip side, when you do an integral, when you have integral f of x dx, the dx is serving the same purpose that it did over here in indicating that you're integrating with respect to the variable x. And just like with the derivative, where you enclose the function that you were differentiating between two parentheses, you also have a similar kind of syntax here, where you're enclosing the function f of x that you're going to integrate between two symbols, the integral sign and the dx. So don't forget to write your dx or your dt at the end of your intervals. You might get the right answer, but leaving out the dx or the dt it's sort of like writing a sentence and using improper punctuation. It looks wrong, and it can actually lead to some confusion and to mistakes. So put it there, and I'll thank you. Okay, we've got this power rule for integration, and it's time to talk about some other integration formulas. And remember that every time you have an integration formula and you're wondering if it's really correct, differentiate the answer and see if you get the integrand. So our first differentiation for integration formula is this one. Here, k is a constant number, and the formula is the integral of k dx equals k times x plus c. And to check that, differentiate the k times x plus c, and the derivative of k times x is just k plus 0. It just gives you the k there. So with this formula, you would say that the integral of 5 dx is 5x plus c. The integral of pi dx is pi x plus c, and so on. Now, here is our power rule for integration that we just mentioned on the previous slide. And my goodness, I forgot to put the plus c right there. That is a typo. And this also only works for n equals, or n not equal to -1. So you don't want to get the 0 on the denominator. Now, you might ask, what would you do if you had x to the power of -1, where n really was equal to -1, and you couldn't use this formula? Here's what you would do. If you ever had the integral of x to the power of -1 dx, that would be the integral of 1 over x dx. And so the answer to that should be an antiderivative of 1 over x, or all of the antiderivatives of 1 over x. So you're looking for a function where if you took its derivative, you get 1 over x. And ln of x plus c does the job. We know the derivative of ln of x is equal to 1 over x. So this is what you would do if your n was actually equal to -1. You'd use this formula instead of the power rule for integration. Now, I said that you would use this formula, but there's something slightly off with this formula that we're actually got to do a little tweak to it. Notice here that you have the integral of 1 over x dx equals ln of x plus c. And think about the function 1 over x. Its domain is all real numbers except 0. But over here in the answer, we got ln of x, and its domain is just the positive real numbers. So we got a problem there because this function we're integrating and the antiderivative, they have different domains. So what we're going to do to correct that is this x right here, we're going to make that absolute value of x. And the text talks about how if you differentiate ln of the absolute value of x, you get 1 over x. So this is our formula. And this is the last word on this one. The integral of x to the power of -1 dx equals the integral of 1 over x dx, which is ln of x plus c. And this is what you do if n equals -1 in the previous formula. You use this formula. What else do we have? Well, the way this works is every time you have a differentiation formula, that gives you an integration formula. We know that the derivative of e to the x plus c is e to the x, so that tells us that the integral of e to the x dx is e to the x plus c. What about the integral of sine of x dx? Well, a little reverse thinking would work this way. If you had minus cosine of x plus c, its derivative would be minus sine of x plus 0, which is sine of x. And that gives us an integration formula. Write it down and commit it to memory. The integral of sine x dx is negative cosine of x plus c. And for the same reason, the integral of cosine of x dx is sine of x plus c, because if you took the derivative of sine of x plus c, you get your cosine of x. So this is the antiderivative of cosine of x. Notice how the integration formulas for sine and cosine are similar to, but differ from the differentiation formulas. We had the derivative of sine of x was cosine of x, and the derivative of cosine x was minus sine of x. But when we're taking the antiderivatives, those signs are reversed. Now, you would like to have a formula for the integral of tangent x dx, but that's not quite the way this is working. because we're running known differentiation formulas in reverse. The derivative of tangent x plus c is secant squared x. So that tells us that tangent x plus c is an antiderivative of secant squared x, meaning that the integral of secant squared x dx equals tangent x plus c. So you see how that's working? And likewise, we know that the derivative of cotangent of x is minus cosecant squared x. So consequently, the derivative of minus cotangent x plus c equals cosecant squared x. And that gives us an integration formula. The integral of cosecant squared x dx equals minus cotangent x plus c. What else do we have? Well, the derivative of secant x is secant x tangent x. So the antiderivative of secant x tangent x is secant x plus c. You differentiate the answer, and it gives you the integrand. And our last trig function in differentiation formula in reverse would give us that the antiderivative of the integral of cosecant x cotangent x dx equals negative cosecant x plus c. And that's correct because if you took the derivative of negative cosecant x plus c, you'd get cosecant x cotangent x. We'll move on to another list, a continued list of these integration formulas. But make note of these, and you're going to commit these to memory just the way you committed all of the differentiation formulas to memory. And really, not just commit them to memory, but internalize them. And of course, the way that happens is working lots and lots of problems. More formulas. Because the derivative of sine inverse of x plus c equals 1 over square root of 1 minus x squared, we get an integration formula. The integral of 1 over square root of 1 minus x squared dx equals sine inverse of x plus c. And we get another one for tangent inverse of x. We know the derivative of tangent inverse of x is 1 over 1 plus x squared. So that would mean tangent inverse of x is an antiderivative of 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared dx equals tangent inverse of x plus c. Now, the other inverse trig function differentiation formula we know is that the derivative of secant inverse of x is 1 over the absolute value of x squared of x squared minus 1. And that would suggest that the integral of 1 over absolute value of x squared minus 1 dx is secant inverse of x plus c. And that's a correct formula. However, we're going to do something that's real similar to what we did with ln of x. By the letter of the law, we've just run our differentiation formula in reverse here. But the way this normally works is that if you're finding an antiderivative of a function, it's probably like, that looks like this one, it's probably going to come to you in a way that doesn't have the absolute value of x there. So we're going to correct that, and you can read this, the details of this in the text. We're going to correct this by removing these absolute value braces and putting them right here. So I'm about to do that. Here we go. We removed them here, and we put them right there. And you can check, if you want, you do have to do it piecewise, but check that the derivative of secant inverse of the absolute value of x plus c, it really is 1 over x, square root of x squared minus 1 dx. So this is the integration formula that we're going to use. I always find that these three integration formulas are a little bit surprising because if you're looking for the antiderivative of 1 over 1 plus x squared, for instance, you seem like you're pretty far from trig functions there. That looks like a rational function. It's rather surprising that the antiderivative or integral turns out to be an inverse trig function. Now, another formula that we have that runs a differentiation formula in reverse is this one. The integral of b to the power of x dx equals 1 over ln b times b to the power of x plus c. Now that may look strange for a moment, but you know how to check it. You would differentiate the 1 over ln b times b to the x plus c and see if that gives you b to the x. And if it does, this is a correct formula. Well, ln b is a constant because b is a constant. So 1 over ln b is a constant. So when we differentiate this function using the constant multiple rule for differentiation, we get 1 over ln b times the derivative of b to the x. And remember, that's ln b, b to the power of x. And the ln b's cancel and just get b to the power of x. So differentiating this answer gives you your b to the power of x. So this formula is correct. So for instance, the integral of 2 to the power of x dx would be 1 over ln 2 to the power of x plus c. Now here's a slightly more general formula. We would call this one, and we do call this one, the constant multiple rule for integration. It says that if you ever have the integral of k times f of x dx, that's the same as k times the integral of f of x dx. That you can factor the k, the constant k, out of the integral sign. But it has to be a constant. You can't factor out a variable from the integral sign. You have to factor out a constant. And this comes from just running the constant multiple rule for derivatives in reverse. And we also have a corresponding sum difference rule for integration. The integral of f of x plus g of x dx is the integral of f of x dx plus the integral of g of x dx. You can break this single antiderivative into two simpler, potentially simpler, antiderivatives added together, or two simpler integrals added together. And it should be clear that this plus, it could also be a minus as well as a plus. So we'd call this the sum difference rule. Now, I've noted these two rules here, but you're probably going to get to a point very quickly where you don't even think about these. This process of breaking things up is really kind of automatic when you get used to working these problems. Even though we have a constant multiple rule and a sum difference rule for integration, it's a little unfortunate that there's no product or quotient rules for integration. The integral of f of x times g of x, there's no formula for that. And that's just an unfortunate fact. And we have to get by on what we have available to us. A few examples. How about the integral of 5x cubed plus 1 over x plus 4 over x cubed plus 7 dx? And I'm going to do this in the way that you're probably not going to like to see it done, and then we'll do it differently forever after, the way you want to do it. We're going to totally break this up using the sum difference rule and the constant multiple rule and do it step by step in excruciating detail. So first of all, using the sum difference rule multiple times, this integral would be the integral of 5x cubed dx, that's the integral of the first part, plus the integral of 1 over x dx, plus the integral of 4 over x cubed dx, and I'll put that right here. Now, notice that I've brought the x cubed on the bottom up to the top as a negative power, because you can see that we're probably going to want to use the power rule for integration momentarily. And then lastly, we have the integral of 7 dx. So we've broken this complicated integral up into 4 simpler integrals using the sum difference rule. Now the next thing that could happen is that these constants of multiples of 5 and 4, they could factor out of their integrals. So the 5 comes out of this one, and the 4 comes out of that one. And then we can use our integration formulas term by term for this. We have this first integral, and it's the integral of a power, so we use the power rule for integration for that one, and we get 5 times 1 over 3 plus 1, x to the power of 3 plus 1. And then we have the integral of 1 over x dx, and we know that's ln of the absolute value of x. Then we have 4 times the integral of x to the minus 3 dx, and using the power rule for integration, the integral of x to the power of minus 3 dx is 1 over negative 3 plus 1 times x to the power of negative 3 plus 1. And then we have the integral of 7 dx. And remember the very first integration formula that we talked about a couple of slides ago? So that the integral of k dx is kx. So the integral of 7 dx is 7 times x. Now, always when you are computing antiderivatives, you're just going to put a plus c at the very end, which could be any constant. And cleaning that up, we get an answer of 5/4 x to the 4th plus ln absolute value of x minus plus 4 over minus 2 x to the power of minus 2 plus 7x plus c. And further cleaning that up, the 4 over 2 is a 2. Bring that negative 2 power down to the bottom here. And there is our answer. Now, perhaps this was too much detail, more detail than you wanted. Take heart, because what happens is that you'll very quickly get so used to these that you tend to do them in one step often. So the way you typically work this problem is you'd say, okay, I've got the integral of 5x cubed plus 1 over x plus 4 over x cubed plus 7 dx. You go, oh yeah, power rule for integration times 5 would be 5/4 x to the 4th. You do all of that in your head. Then you go, okay, antiderivative of 1 over x is ln absolute value of x. And then mentally you'd say, oh, well, 4 over x cubed, that's 4x to the power of minus 3. Power rule for integration would be, and you just do all of this in your head, and you get negative 2 over x squared. And then plus the antiderivative of 7, you know that's 7x, and plus c. So typically you do all of this work in one step, or maybe 2 steps to convert the powers and so on. But there you go, that's perfectly acceptable. Likewise, if you had the integral of pi over 1 plus x squared dx, you'd look at that and you'd say, oh, well, that's just pi times 1 over 1 plus x squared, and the antiderivative of 1 over 1 plus x squared is tangent inverse x. So you'd get the constant of pi times tangent inverse of x plus c. Let me call to your attention at this point that a lot of times this is written as follows, that dx at the end, that'll come up as if it's an actual, I think of it as like it's the closing parenthesis, but sometimes you'll look at that as a actual mathematical symbol that you can multiply times the pi, and you'll write this as the integral of pi dx over 1 plus x squared. And same process as before, you'll know that's pi tangent inverse of x plus c. That pretty much wraps it up for today. Let me summarize what we've done. Integration is the reverse process of differentiation. From a function big F of x plus c, if you differentiated it and got f of x, that would mean that this big F of x plus c is an antiderivative of the little f of x. And going from the antiderivative to the derivative, that process is called differentiation. Going backwards is called integration. And the integral of f of x dx equals big F of x plus c means exactly the same thing as the derivative of big F of x plus c equals little f of x. And I promised you I would put this relationship in a double box many times, and you've seen it, 3 times in today's lecture. As we continue in Chapter 5, we're going to deal with integration more and more. In fact, Chapter 5 is all about integration. And there, this relationship in this box will come up time and time and time again. If you're ever in hot water, so often if you think about what's going on here, it'll tell you what to do. But for now, the thing to do is get lots of practice. A good thing to do would be to just go through the textbook, look at odd-numbered problems where it says, find this integral, find that integral, using the formulas that we talked about in class today and that you'll read about in the book. Just do them. Do lots of them. They're quick. Sometimes you'll stumble. Sometimes it looks like it's something new, but you'll figure it out. And doing that is essential for your survival. You'll get good at it very quickly. And as you're working those problems, I want to emphasize that if you're ever working out the integral of f of x dx and you get some big F of x plus c and you're not sure if that's the right answer, you can always check. Take the derivative of the big F of x plus c, see what you get. If you got the function you were integrating, you did it right. So do lots of those problems. Enjoy. I'll look forward to seeing you next time. So goodbye.